The objective of this talk is to study what happens when a stochastic process is input to a linear time invariant system and to study the properties of its output. So this is a case. X dt is a stochastic process, assume it's stationary. This is a linear time invariant system that is described by its impulse response h dt. And in output, what we have? We have another stochastic process that is derived by the input through the convolution. Well, the convolution basically is a linear combination. So in general, when the filter impulse response is very long, so that it takes independent samples of the input, for the central limit theorem, the output, so y dt, tends to be normal distributed. This is not always the case, but in the majority of the case, the output of the stochastic process is normal, whatever the input. We can tell even more, because if we want to evaluate the mean value of the output, we apply the property of the mean value and the convolutions that are linear operator and can be commuted, and then we say that the mean of the output is the mean of the input multiplied by the area of the filter. Well, what about the other properties of not the mean, but the autocorrelation and the cross spectrum? The cross spectrum is very easy to derive, because if we make the cross spectrum between the output here and the input, that is, this is the definition, but the output is the input multiplied by the filter, the Fourier transform of the filter, and we get this very simple property, that the cross spectrum output-input is the power spectrum of the input multiplied by the filter. And of course, if we do the inverse transform, we get that the cross correlation between output and input is the convolution between the autocorrelation of the input and the filter. It's pretty interesting to tell what happens if the input is white, because if this is constant, the cross spectrum will be the filter but for a scale, and the autocorrelation will still be the impulse response of the filter but of the scale. And for the same reason, we can tell that the power spectrum of the output is the power spectrum to the input multiplied by the squared amplitude of the filter. So from the power spectrum, we don't see the Fourier transform of the filter, we see the square amplitude that is less. And of course, if the process is white, the power spectrum of the output is just the square amplitude of the filter. So let us make an example. Let us consider a discrete process whose impulse response is made just by 3 samples, 3, 2, 1, and in input we have a white process. Then let us, for example, compute the power of the output. The power of the output is the integral of the power spectrum, so is the integral of the product of the input power spectrum and the square amplitude of the filter. But as the power spectrum of the input is constant, then we just integrate the square amplitude of the filter, that is the energy. So it means that if the process in input is white, then the output will be scaled by the energy of the filter, that is the sum of the square value. 9 plus 4 plus 1, it is 14. This we can show in this simulation, in which we have 4 realizations of the input, that is a normal distributed process with 0 mean and unitary variance. We have the filter, 3 to 1, and we have the output. The input is white, but the output has some memory, so some correlation. And we see that the scaling term is the square root of 14 in standard deviation. And as well, we can compute the other statistics. So, for example, if we estimate the auto and cross correlation, on the left we have the estimate of each sample, of each realization, and on the right we have the average of the estimate of the 4 realizations, and the rows corresponding to the input process, the output process, and the cross correlation between the output and the input. So, for example, the average autocorrelation of the input is a delta, as we expect, And much more interesting is that the average autocorrelation of the output is the autocorrelation of the filters that we can compute in a theoretical way. But the most important fact is that if we do the cross-correlation between the output and the input, we see that something resembles very much the filter that is 3, 2, 1, 0. So from the cross-correlation output-input, we have the filter maybe but a constant scale. For the power spectrum density, it is the same, but we apply the Fourier transform, that is the periodogram. We see if we compute just the Fourier transform of the single realization, that is not so accurate as averaging the Fourier transform. So the average of the input is very close to be a constant because it's white. The average of the output is a square value of the filter that I draw in red, and it's very close to the square value of the filter, but much more interesting that if we compute the cross spectrum that is complex, we compute its amplitude, that is really the amplitude of the filter that is represented in blue here, and we compute the phase that is here. You see how much the phase goes very close to the phase of the filter. So only the cross spectrum gives us the information about the phase of the filter. And now let's see how we can use this property of the linear time invariant filter of stochastic process to evaluate the accuracy of the mean estimator. We have already analyzed the mean in the discrete case. Now let us consider the continuous mean. The continuous mean estimate, the sample mean estimator, is done by averaging in an observation time and dividing by the observation time. The point is that how good is this estimate, so how good is the mean value of this number and how good is converging to the mean value. So we desire the standard deviation to be 0. And in order to evaluate this, we can use the principle we describe by considering that we have an input process, we have a filter that is basically a rectangle, means that we sum over the observation time and divide by observation time, and we have the output. However, we compute only a single sample of the output. So this is the mathematical formulation, and this is the mean estimated as a single sample of the output. Then we can tell that the mean value of the estimator, that is the mean value of the process y, is the product of the mean value of the input process times the area of the filter. As the filter has a unitary area, the mean of the output is the mean that we want to measure. So far, the mean is very good because it is unbiased. To compute a variance that is a little more complicated, because we must compute the variance of the output of a filter. And this variance is the difference between the autocorrelation and the square mean value, that is, however, the square mean value of the process we want to estimate. So basically, the autocorrelation is the integral of the power spectrum, so is the integral of the power spectrum of the input and the square amplitude of a filter, that is a sin squared. Just in order to make it short, we have to compute the integral of a product of the blue, that is the power spectrum of the process we wish to estimate the mean, and the green, that is the square amplitude of the filter. Now we can say that these two shapes can be one very narrow and the other very large. But in principle, if this filter, the mean, is very long in the time domain, then in the frequency domain becomes very, very short, and then when we multiply these together, the blue is almost disappear, and we pick up only the mean value. So let us consider these two cases. One in which the observation time is very, very big, so it's much bigger than the duration of the decorrelation of the process. Here we see we are considering, for simplicity, a white process, so a constant power spectrum. Well, if the green, that is the square amplitude of the filter, is very narrow, and we multiply by a constant, we have only the green signal. And then when we compute the area, we got exactly the power spectrum in the origin, that is sigma x divided by bx, divided by the area of the filter, the observation time. So it means that the accuracy decreases with the product of the bandwidth and the observation time. And observation time is very large, the accuracy is very, very good. In the other case, we consider when the observation time is so small that the filter is so large that actually what we get when we filter is exactly the original process. So basically the filter is doing nothing and the mean is just the power of the process. So we have two cases now. In the first case, the product of the bandwidth of the process and the observation time, that basically is the number of uncorrelated sample is n is large. Now the variance is the power of the process divided by n. This means that we are observing the process changing, and then these changes are captured by the n independent sample. In the second case, the time bandwidth product is very, very small. It means that we can have a lot of sample, but basically we observe only one single value of the process. So even if the samples are hundreds of thousands, no matter, the variance will be very bad and will be equal to the variance of the process. Then we can do at last a closed form evaluation of the accuracy that I have plotted here, just by considering the discrete case. So the mean estimator we already considered in a previous talk. But now we consider that we can have also correlated sample. And this is expressed by the observation time. So when the observation time is very, very large, we see that the variance of the estimate basically is sigma squared, that is the power of the process, divided by the number of independent samples. But when the observation time is very small, that we don't see observation time, so we don't see correlated sample, so is less than the decorrelating time of the process, then the variance is just the variance of the process that is doing nothing. So this is an example of how a very complicated evaluation can be done in a very simple method by using the filtering of stochastic processes.